at the how and why of what causes changes in motion of an object, specifically the idea behind forces, what we call dynamics. To help us get started by looking at this, we'll start by looking at the basis for dynamics, what are known as Newton's laws, the topic of 2.1. So an introduction to forces, a force is any interaction between two or more objects which causes the objects to change motion or to accelerate. So in Unit 1 we looked at what happened if an object accelerated and how we could break the motion of an object undergoing acceleration, but we didn't look at what caused the acceleration. So now we're looking at what caused the acceleration, what we know as a force. So there's a correlation, direct correlation between forces and acceleration, specifically that the larger force you apply, the larger acceleration your object will have for a given mass. So in this case right here, if we double our force, we're going to subsequently double the acceleration of our green car right here. Since the force applied to an object has both a strength and a direction, forces are vector quantities. So not only can we double the force here, but we can also apply force in different directions. So here we're applying it to the left, or excuse me, to the right, but there could be a case where we apply force to the left, thus causing our car to accelerate backwards. So here we're going to go through some types of forces real quick. So first type of forces, class of forces that we have are non-contact forces. The gravitational force, what we label with F subscript G or W, is the first non-contact force that we're most familiar with. This force causes attraction between two or more objects that have mass, hence why you fall to the earth. It's a non-contact force because you and the earth are attracted to each other, regardless of there being any contact between you and the earth. And then we have the electrostatic force, which is what we'll study in Unit 9, denoted by F subscript E. This force causes attraction or repulsion between electrically charged objects, i.e. opposites attract, likes repel. There are many other non-contact forces in nature, specifically on the subatomic level, but these are two main forces that any introductory physics class will have to deal with. The subatomic forces come into play when, well, you've learned quantum mechanics. So now we get to contact forces. The first one we have is what we call the normal force, F subscript N. This is a force. This is a contact force that results when an object comes into contact with a surface. The surface will exert a force on the object, preventing the object from falling through the surface. The word normal means perpendicular, as the force will always be perpendicular to the surface. The idea being is that the surface is going to push outwards away from itself on your object, so the force will always be perpendicular to the surface. So please note, like right here, we have this object that's on an incline. The normal force in this case is acting perpendicular to our incline on the object, keeping our object from falling through. So whenever you have two objects in contact, they'll always exert normal forces on each other, perpendicular to the surfaces of contact. So the second type of contact force we have is friction. Friction is a force that is a result of microscopic collisions between surfaces moving against each other. So if you look at any surface, not every surface is perfectly smooth. There's always some roughness here. So what happens is if you move an object, let's say to the right, in this case right here, collisions between the ground and your object will exert a force in the leftward direction or opposite the direction of motion. So in this case, friction acts to the left. So the force always opposes the direction of motion or attempted motion. If our object here were moving to the left, then friction would act to the right in order to counteract its motion, the object's motion. So some other forces that don't exactly fall in classes of forces, air resistance, which we'll look at in 2.2, and tension, represented by the letter T. Tension, when you pull on a rope, the force is transmitted via tension. So tension is the force exerted along a tense material, such as a rope or maybe the muscles in your arms, so on and so forth. So in order to help us visualize forces, we employ what are known as free body diagrams, or FBDs for short. So the idea behind a free body diagram is first we want to recognize the forces acting on the object, including the relative strength of each force and the direction of each force. We really want to make sure we have free body diagrams down, so we'll get more practice with this in class. We'll take a look at an example of this car right here, but we'll get a lot more practice with this in class. We draw our forces with appropriate lengths to represent strength, and starting from the center of your object, minus friction. Friction always starts at the ground because that's where friction acts at, okay? And we'll go over friction in more detail in 2.3. So when we want to draw our forces with appropriate lengths, in order to represent the relative strengths of our force vectors. So friction would generally tend to be weaker than, say, the force due to gravity, so we would draw friction as a shorter arrow than the force due to gravity. We'll see this in an example in a bit. And again, like I just said, if friction occurs between two surfaces, the friction vector will be drawn where two surfaces meet. Oh, and those are the 3 points here. All right, so let's see what those 3 points look like in action. So, what we're going to do here is we list the forces that are acting. We identify the forces are acting first off. So let's say we have a car that's moving to the right and braking, hence why we see the smoke coming out of the tires. We want to know what forces are acting in this case. So we know that gravity is always going to act because there's always going to be gravitational attraction between anything that has mass and the Earth. So we can draw Fg pointing down. We know a normal force, Fn from the road, pushes up on our car and keeps it from falling through. This normal force is going to counteract, in this specific case, the force due to gravity, so it will have an equal length to the force due to gravity. In general, the normal force does not counteract the force due to gravity, so we cannot always draw it that way. That's a big misconception that we'll go over in class to make sure we have a strong handle on. The braking force of the car, if our car is braking, pushes against the motion of the car, so Fb. And the braking force tends to be weaker than force due to gravity, so we draw this a little bit shorter. And also we recognize that there's going to be friction between the tires and the road. So as a result, we draw a friction arrow with the little lowercase f for friction acting to the left. This friction arrow is the smallest of arrows since it tends to be the weakest of the forces acting. So friction will always be weaker in gravity, so the arrows of friction is always going to be shorter than the force due to gravity. And this is a basic summary of how we do a free body diagram for this example of a car braking right here. Newton's first law. So what we first addressed is a new definition, what we call a net force, the sum of all forces acting on an object. We represent the net force in the x direction with sigma fx and the net force in y direction sigma fy. This should say y right here, not x. Again, the idea being, going back to projectile motion, is that our x and y directions are separate and independent of each other, so we have to sum the forces in the x direction separate from summing the forces in the y direction. We cannot just sum the forces all together at once. They have to be broken up into their respective directions. So, if we look at these two examples right here, we'll see that we have a tug of war, and we can imagine a little flag in the center right here, okay? If both sides are pulling with 300 newtons, one side to 300 newtons to the right, the other side 300 newtons to the left, we can recognize that there are individual forces acting on our object, specifically the flag in the center if we imagine it there. However, the net force acting in the x direction is 0. There's 300 to the left and 300 to the right, and thus our forces are balanced. So what we expect to see is, since both sides are pulling with equal amount of force, we would expect to see that this red flag just stays right in the middle and doesn't move at all. So we can make the observation that individual forces are acting in a tug of war, but the net force is 0, hence the flag will remain at the center. In addition, if you've ever watched a sport of curling or ever watched a hockey puck slide across ice, the curling stone or hockey puck seems to slide indefinitely, especially if people use brooms out front to smooth out the ice and reduce the friction. The idea being in curling is that if you smooth the ice as much as possible, you're reducing the friction as much as possible, and hence your object will stay in motion for a longer period of time. The curling stone will stay in motion for a longer period of time. So what we can say is that in an ideal case, if we take the extreme where there's no friction, if there's no friction, our curling stone / puck would continue to move at a constant velocity. There'd be no friction acting, so our curling stone will continue to move indefinitely at a constant velocity. In the y direction, say up to down, the normal force would balance the gravitational force acting down on our curling stone. So in both of these cases, we can generalize this to what's known as Newton's first law of motion. An object will maintain constant velocity, like the curling stone, or remain at rest, like our flag in the tug-of-war game, unless a net external force is acting upon the object. In both of these cases we talked about, there's no net external force. In this case, the forces are balanced, and in the curling stone case, there's no friction present, and the normal force counteracts the force due to gravity. So as a result, an object will maintain a constant velocity or remain at rest unless a net force is acting upon the object, meaning that the acceleration of the object is zero. There's no change in velocity occurring. This is also known as the principle of inertia. The more inertia an object has, the more likely it is for the object to maintain its current state of motion. Inertia is quantified in physics by mass, so it represents resistance to changes in motion. Again, we can see this in everyday life, that the more massive an object is, the more force we have to apply to that object to get it to a given acceleration. I.e., pushing a shopping cart would be a lot harder, would be a lot easier than pushing a car, because the car has a lot more mass and hence inertia than the shopping cart. That's just a very ridiculous but simple example. So now this brings us to Newton's second law. Newton's second law states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to the mass of the object. So acceleration is proportional to net force and inversely proportional to the mass of an object. The units for force are newtons, named for Isaac Newton, who formulated, well, Newton's laws. So we captured this expression right here in the equation sigma f divided by m equals our net acceleration. This is how it appears on your equation sheet, on the AP Physics 1 equation sheet, in the way that you should interpret it mathematically. Now, the more practical way that we use this for problem solving is a form that you may have heard before, F equals ma. But it's not just any F or any individual force acting, it is the net force acting on our object. These statements right here capture everything that we've talked about so far, going back to the first slide where we defined a force as something that causes an acceleration in an object, and going back to the last slide where we talked about the principle of inertia, where the more mass an object has, the more resistance it has to changes in motion, captured by that inverse proportionality between acceleration and mass. So this brings us to the distinction between mass and weight. So mass is a property of an object that measures the amount of matter in an object. It remains the same independent of location. So we tend to confuse mass and weight a lot. By using Newton's second law, we can distinguish between mass versus weight. Weight is a measure of the gravitational force on an object, hence it changes depending on the acceleration due to gravity at a certain point. So the equation we have for weight, which is W, or the force due to gravity, is mass times acceleration, where we replace acceleration with the acceleration due to gravity, which is g. So Fg, the force due to gravity, or your weight, is equal to mg. So here's a slide to demonstrate here. If weight is the measure of the effect of gravity on the object, where mass is the measure of amount of matter in an object. So if a person is on the Earth and on the Moon, they'll have the same amount of mass because they're going to have the same amount of matter. That does not change from location to location. However, the person will have a different weight on the Earth than on the Moon because the acceleration due to gravity on the Earth is different from the the acceleration due to gravity on the Moon. Specifically, the acceleration of gravity on the Moon is less than that on Earth, so on the Moon your weight will be less. Hence why, if you've ever seen the videos of people walking on the Moon, they seem to float on the Moon, which is not true. They still fall and come back down to the ground. It's just that their acceleration due to gravity is less on the Moon than on the Earth. So problem solving with Newton's second law. Here are the main strategies for problem solving Newton's second law. We're going to draw a free body diagram representing the forces acting on your object. We identify what the problem is asking for you to solve. In most cases, it's an acceleration or a particular force, but sometimes they like to ask for mass or different quantities, so we got to watch out for that as well. We sum the forces in the x direction and the y direction separately. X direction and y direction forces act separately, so we cannot have the x and y direction forces added together. Thank you, we have to add them together separately. Fourth, we're going to use Newton's second law to solve for the unknown quantity. We apply Newton's second law to the sum of the forces that we did in step 3 in order to solve for an unknown quantity. If any of y'all were wondering what that sound was, well, another teacher came in and just gave me a cookie for the first day of school. So, example 1, problem solving with Newton's second law. Two boys push a 5-kilogram box on a frictionless floor. James pushes the box with a 10 Newton force to the right. Lewis pushes the box with an 8 Newton force to the left. What is the resulting acceleration on the box? So this is a fairly straightforward application. We'll look at more difficult scenarios in class, but again, the idea here is we just want to wrap our head around the problem-solving process. So the first step that we're going to do here again is we draw the net forces acting on our object. So we can say FL is the force of Lewis that pushes to the left. We can say Fj is the force of James pushing to the right. Notice that James pushes with force of 10 newtons while Lewis pushes with force of 8 newtons. Hence, the vector arrow for Fj is slightly longer than the vector arrow for Fl. Lastly, we always have the force due to gravity, and since we're on the ground, on flat ground in this case, our normal force is going to act perpendicular to the ground, so it will act perpendicular to the ground and also counteract gravity in this case. But again, in general, the normal force does not counteract gravity. It's just a result of the specific scenario here. So 2, we're looking for acceleration. The problem asks us to identify acceleration. Specifically, since we're given forces in the left and right direction, that indicates we're going to find the acceleration in the x direction. So now if we move on to step 3, we're going to sum the forces together in the x direction and y direction. Okay, so we have the force of James minus the force of Lewis. We have the force of Lewis drawn with a minus here, since it acts to the left, equals mass times acceleration, ax, in the horizontal direction. Now in the y direction, we have minus Fg, since Fg acts downward, plus the normal force equals mass times acceleration in the y direction. Well, in the y direction, our box is just at rest. It's just sitting on the ground. It's in the x direction that our object is going to be accelerating. So our vertical acceleration is 0, hence we get 0 acceleration. So if we wanted to solve this, we could solve and say that our normal force is equal to force due to gravity in this case, but we don't have to. Problem's not asking for it. So in this specific scenario, we now go step 4. We're looking for horizontal acceleration. So we plug in 10 newtons for Fj, 8 newtons for Fl, and we plug in 5 kilograms for our mass. So we have 2 newtons equals 5 kilograms times Ax, or 0.4 meters per second squared equals Ax after we solve. Thus, the acceleration of the car is 0.4 meters per second squared to the right. The idea being is that since our acceleration is positive, that indicates a rightward acceleration, which would make sense since James pushes to the right with a greater force than the force with which Lewis pushes to the left. Lastly, we come to Newton's third law, which states that if two objects A and B interact with each other, they will exert forces equal in strength but opposite in direction on each other. You may have heard this in a more common form. For every action, there's an equal and opposite reaction. So if we have two objects A and B that collide, let's say they're two billiard balls, the force of B acting on A is going to be equal in magnitude to the force of A acting on B, but opposite in direction, hence why we have the negative sign right here. We'll spend more time with this in class via an in-class discussion because there are a lot of misconceptions regarding Newton's third law. But a brief example of Newton's third law is looking at a person who is in a canoe. So when a person paddles in a canoe, that propels a canoe forward. So what specifically about the paddling is causing propulsion? Well, when the person's paddling, they're pushing the paddle back, which exerts a force to the right on the water. As a result of Newton's third law, the water is going to push back on the paddle and hence the canoe to the left. So as a result, there's going to be an equal and opposite force from the water acting on the canoe, which causes the canoe to accelerate to the left. Hence causing the acceleration and subsequent motion of the canoe. And these are the main concepts behind Newton's third law.